Okay, so continuing our discussion about substitutions, there are really two kind of approaches to this, and they're both good. They're both important to know, but rather, I think most of us find that one of them is easier than the other, and it depends on who's teaching you this and what their preference is as to how they present it. So I'm going to present it both ways, and then kind of talk to you about which one I favor and why. So the two methods of doing a substitution. And again, they're both good. The first one I'm going to call just spotting the derivative. And the first one is just like that example, our prior example from the introduction. The second way of doing it is where the derivative, quote, reduces away. And we'll look at that in a second. But spotting the derivative, you just recognize the derivative, and then you substitute for the entire differential expression. So what do I mean by this? Okay, so first things first, let's identify what we think our u is going to be. Well, our u is going to be, and I don't know, I had a green pen going, so we'll just let this ride. Stop. Sorry about the navigation thing, left-handedness on this tablet. Okay, so our u, what do you think our u is? Well, again, taking that hint to mind, I see that this is kind of trapped inside. So let's just see what happens. 3x squared plus 4. And looking ahead to say, hey, I want to see a function and its derivative. I see that 3x squared plus 4 has derivative 6x. So I'm like, yes, this is good. So I'd say, all right, well, the next thing to do is to calculate its derivative. Well, what is its derivative? du, derivative of u with respect to x, dx is 6x. But by multiplying both sides by x, I can put this into that differential form where we have du is equal to 6x dx. But that is cool because 6x dx is the same thing as du is. So I can substitute this thing in directly. And making our substitution, okay, so we'll just call this equal to circle star, and we'll continue circle star down here. We'll make our substitution, and we'll see that everything highlighted in yellow is going to be replaced with du. And so all I need to do is replace this u in for 3x squared plus 4. That's going to leave me with u to the fourth du. I'll just emphasize that's happening. Du can be replaced 6x dx. And if you're thinking to yourself, that's great, but what if that was like 12x out front? That's where this gets a little bit harder, and this is where the second method kind of can be very, very helpful as well. Because you may be thinking, well, great, this example was tailor-made to work like that. What happens when it isn't? And some people are, the answer is that some people are great at this, and they can say, well, that's just 2 times the derivative, and they can work with it like this. But I've never been that great at it, and I'm kind of spoiler alerting, telling you that I prefer the second method. Okay, so let's just finish this thing out real quick. To do that, we need a pen, not a highlighter. Equals 1/5 u to the 5th power plus c. Reversed my substitution. 1/5 times u was equal to 3x squared plus 4. That's to the 5th, everything to the 5th power plus c, and we've done it. We've got our answer. So, all right, I already spoiled it. I prefer the other way. So once again, we're going to make this equal to circle star so we can pick that up later. And we're going to figure out that our substitution is going to be the exact same. U is equal to 3x squared plus 4 because I see a function and its sort of derivative, 6x. But mostly I just see that that expression is inside something to the 4th power. So I'll give it a shot and see how it goes. Once again, it doesn't matter. The steps are the same. If you make a substitution, you have to relate the differentials. And so du dx, derivative of u with respect to x, is 6x. But here's what I like to do here. I like to just strictly substitute in for the differential. Okay, so what do I mean by that? Well, I can take this du dx expression, multiply it by dx on both sides to get du equals 6x dx. And then I could divide it by 6x to isolate that dx expression. Du over 6x is equal to dx. So now I'm going to replace dx with this entire expression, and we're going to see what happens when we do that. So once again, this is, oh no, that's wrong. We need a pen, not a highlighter. Once again, to start our substitution, we're going to start by putting our u in and say, okay, circle star, back to our integral. Our integral is I'm leaving space deliberately here. I'm going to write that 6x, but I want to just start by substituting in u. Well, I replaced 3x squared plus 4 with u, so that's u to the 4th power. Now, I highlighted that I'm going to replace the dx using this expression, algebra, the derivative algebra into shape to solve for dx. Well, that doesn't say anything about this 6x out front, so I'm just going to leave it there. Okay, so now I'm ready to substitute in for dx. What is dx? Well, dx is du over, 6x. I'm going to highlight that just for good measure to show that that's my substitution. Okay, so now, according to this method, I called this the derivative reduces away method. Well, I've got a bunch of things. Again, you can think of those differentials as kind of being multiplied together, and I work with them as if they're, you can do regular algebra with them. So if this is multiplied with this, well then, sure enough, 6x reduces with 6x. And my derivative goes away. And I end up with the exact same integral of u to the 4th du equals ... We did it above, so we're just going to borrow our work from above and go straight to the punchline of 1/5 3x squared plus 4, all raised to the 4th power, plus c, because it really is the same exact integral that we did above. So now this, I prefer this method because if I had something like, I don't know, 7x here, I could use this method and the x's would reduce away and the 7 and the 6 would just become a constant, which doesn't hurt anything, and I could still integrate the problem. Whereas I think spotting the derivative with that type of a problem would be a little bit more challenging. So let's just leave this here, and then I'll do another example to try and convince you or show you more, or to illustrate more of why I like the derivative reducing away method a little bit better.